Welcome to this second long-range colloquium hosted by the Virtual Science Forum. Since this is the only second one, and maybe we have a lot of new people, let me briefly introduce us, which we, the Virtual Science Forum, are a group of scientists trying to create a sort of free, open access system of virtual scientific communication and collaboration. And this colloquium series is just one component of a broader effort. And I encourage you guys to visit our website for more details. And if you're interested in joining the initiative, or especially hosting your own virtual mini conference, please join our GitHub and Gitter groups and introduce yourselves, and we can tell you more about how to do such a thing. And regarding this colloquium, the inaugural event was last week, 2 weeks ago, excuse me, where we had Liang Fu of MIT. And next week, we're excited to have Vidya Madhavan of the University of Illinois at Urbana-Champaign, for which you can already register on our website. So please see there if you'd like to attend that talk. And a quick note regarding how we're going to do Q&A. You're not able to unmute yourselves, but myself and one of the other organizers will be watching the participants pane, which I encourage you to open via the participants button at the bottom of your Zoom screen. And at the bottom of the participants pane, you can see a raise hand button. And so if you raise your hand, your name with the raised hand will go to the top of the participants list. When we notice you, we will unmute you and gently let Charlie know that there's a question from the audience. So now, today we have the honor of hosting Charlie Marcus of the Niels Bohr Institute. And he's had a long and noted career in the field of nanoscale physics, and in the past decade or so has focused his efforts on the search for and investigation of topological superconductivity in the superconductor semiconductor materials platform, along the lines of which he'll give us some exciting recent results with a new wrinkle, as you can see on the title of his slide. And with that, Charlie, I hand it to you.
Thanks, Vala. And it's a pleasure to be here. I hope everybody's safe and reasonably comfortable. The talk today is a collaborative work between our group at University of Copenhagen and really the singular effort from Peter Krogstrup's lab, which is up the street at the Niels Bohr Institute and also Microsoft Center, and also some characterization insight from Cam Moeller's group at Stanford. Let me just check before I jump into it. Can people hear me okay? And is the video quality okay? Vala, can you?
It's fine for me, yes.
I see people nodding yes. Okay, good.
Yeah.
Great. Well then, I think I've already frozen, in fact. Isn't that funny? Yeah. Okay. Did this? Oh, no, there we go. Okay. I don't know why there was a time delay between hitting click, but let's see what happens next. I wanted to say that this talk is, if I go too fast and you want to see the slides, it's a archive paper right now, and you can get it and read it. The first author of the paper is Solius, who goes by Sole, via Tekenas. After all these years of being friends with Sole, I still can't pronounce his last name. And this is predominantly his experimental work that I'll be talking about today. The creation of Majorana zero modes for the purpose of topological computing is probably something that was covered in the colloquium last week, and it's a well-covered topic. And I won't spend a lot of time motivating topological quantum computing, mostly because this is a kind of a condensed matter physics talk, I think. The motivation is that a combination of one-dimensional material with strong spin-orbit coupling, proximity effect via a superconductor, and the application of a Zeeman field, which I represent here. And you'll notice the word Zeeman does not start with a letter B. So the difference between a Zeeman field and a B field will be important for this talk. But the application of a Zeeman field transverse to the effective spin orbit field can produce an effective gapless an effective spinless superconductor that has a topological phase. Here you can see the function, I have to move my thing out of the way here, as a function of the Zeeman coupling in the vicinity of Zeeman coupling or beyond, comparable to the superconducting gap, the criterion which normally destroys superconductivity in a material without spin-orbit coupling. A topological phase appears, and a characteristic of that topological phase is the appearance of Majorana zero modes, which are states localized at the ends of the boundary of the one-dimensional system, and they have the interesting property of individually carrying non-abelian exchange statistics, which provides a means of computation which is protected in the sense that no measurement on one of the pair of Majoranas will tell you the state of the pair, that state being whether or not there is or is not an electron associated with that pair. So this inability to detect the state of the pair and that the pair can be braided to perform not a complete set of operations, but enough operations that you can perform protected quantum computing is the basis of the topological quantum computing program. And there's been, because of that, a lot of motivation to create these materials, one-dimensional wires, proximatized by superconductors in the application of a strong magnetic field to produce a topological phase. I emphasize these two papers, which, following the seminal work of Kitaev and others, laying out the principles of this one-dimensional Majorana system. These two papers, appearing almost at the same time, reduced to practice how to implement these using this kind of a system. And it's really following these two papers that's occupied a few groups around the world, mine included, in trying to produce topological states. Let's see if I can switch to the next slide. I seem to not be able to switch slides, actually. Okay. I don't know if this is a Zoom thing or a...
Yeah, this...
maybe I click. Okay, I don't know. Something seemed to happen when I clicked, although now I have no idea how to go backwards. Okay, but I don't know. It's working okay. What I wanted to say was that by now, these one-dimensional wires, which are grown out of 3,5 semiconductors, typically indium arsenide or indium antimonide, has become, you know, kind of an industry, and people are taking the topological states that have been identified through tunneling experiments and producing complex structures and applying dynamics and moving gates around. And although there's still some, you know, general anxiety about the ambiguity of the signatures of Majorana zero modes in these systems, the field has gotten pretty sophisticated based on these wires and gone a long way beyond the original set of ideas. Of particular importance, and you'll see why on the next slide, is the ability to scale these by reproducing a wire structure, not being grown nanowires, but rather by depleting a two-dimensional electron system. Let's see, that's bad. What just happened? I think my thing just crashed. Let's see what happens. I'm not sure if Zoom and...
We've noticed, it has happened to me separately sometimes, that the...
Okay, let's press on where we were. So what I had said was that this idea, which kind of was brought into a concrete form in 2010, and in 2012, first signatures of these Majorana modes detected experimentally in Delft, and then subsequently many experiments from Delft and Purdue and Pittsburgh and Copenhagen and a lot of other places. And it's becoming a complicated system now, and now has moved into the two-dimensional electron gas system where gate-defined structures are possible. This is material grown by in this particular case, Chris Palmstrom was involved, Mike Manfer was involved, Javad Shabani at New York is involved in growing these materials. So the two-dimensional versions of the superconductor semiconductor systems are also yielding these characteristic zero energy states at high magnetic fields. But I want to point out that going up to 1.5 to 2.5 Tesla in order to magnetic fields, these are not magnetic fields that superconductors like very much. And moreover, these are magnetic fields that have to be oriented rather precisely along the axis of the wire. And nobody likes putting 2 Tesla on a superconductor, let alone having to put 2 Tesla on a superconductor with less than a degree of fluctuations in how it's angled. That said, a lot of the theoretical work that's happened in the last few years has acknowledged that when we make these wires, we have to apply a large magnetic field along the axis of the wire for 2 reasons. One reason is that when it's along the axis of the wire, that puts the magnetic field in the correct direction perpendicular to the spin orbit field, which opens up the gap and creates the topological state. That's one good reason to put the magnetic field along the axis of the wire. But the second good reason is because that's a direction in which the superconductor is very thin. And in that direction, the magnetic field does not drive the superconductor normal. So you face this problem, which is that there's one direction in which the magnetic field has to go. So you have to design, if you're a theorist and designing an entire quantum computer around the principle of inducing topological states in all of these one-dimensional wires, whether they're formed out of nanowires or whether they're formed out of two-dimensional electron gas or any other kind of material system. Everything's got to be in the same direction. So here's an entire quantum computer in which all the topological wires are going in the same direction. And this isn't just inconvenient from not being able to have cross-wired topological segments, but they can't even be misaligned. They have to be, dead on accurate, fabricated in the same direction. So this is a tricky requirement for entering this topological protection platform. Particularly when one is envisioning experiments like braiding, where you want to take advantage of these non-abelian statistics and move Majoranas around each other to change their states. And a lot of these formulations have, every formulation that involves braiding involves a branch structure in which something has to be moved out of the way, something else brought across it, something else moved around it, and you have to be able to manipulate the Majorana states they may be more, but the wires have to span a two-dimensional space so that you can move the Majoranas around. Well, that goes directly against the idea of putting the magnetic field in some direction. So, you can compromise. You can put the magnetic field at a kind of a funny angle, as this picture shows, with respect to these Majoranas. But, it's not a good solution if you have transverse wires, which are necessary for braiding, to have magnetic fields pointed in off-axis directions. It drives the system normal more easily. It makes a softer gap. It's kind of no way to run a business, it seems. Now, a long time ago, 2010, the same year that the nano program was kind of laid out, extending work of Fu and Kane, these authors, Jay Sao and Roman Luchin, Tawari and Desarma, envisioned a kind of an analog of the semiconductor version that rather than using an applied magnetic field with its associated difficulties that I emphasized, a magnetic insulator could be used, and that the magnetism of the insulator would impinge upon the semiconductor in a way that would create a spin split density of states via the exchange interaction with the insulator, meaning just scattering off of the surface of the insulator would be enough to induce a effective Zeeman field in the semiconductor and create a topological state. This was the idea, and this was a theoretical proposal, and it kind of sat there, actually, because the magnetic field, everyone has a magnetic field in their lab. but this was kind of something that was not readily available. And alas, I think nobody did anything about it, period. Now, in parallel, from the 1970s forward, there was work on magnetic materials in contact with superconductors. And I'm going to not do an entire survey of that field. I do want to emphasize that there are great review articles on this. Meserve and Tedrow wrote a nice article summarizing their own seminal work from MIT. And also there are several review articles that I'll allude to later on. But just as a kind of a representative of that work, Jagdish is one of the great material scientists growing these films. And here's an example of the material that we'll be focusing on today. This is a rare earth sulfide, Europium sulfide, in a bilayer structure with aluminum. And the tunneling density of states into the superconductor had enough structure to it that from that structure, one could pull out the spin split bands inside of the aluminum, and from that infer the effective magnetic field that the thin film felt that it was in. And the surprising and great feature here is that the characteristic field, depending on the thickness of the film here, if it's 4 nanometers, 5 nanometers, 6 nanometers, 7 nanometer thick film, extends up into the multi-Tesla regime from this ferromagnetic insulator. Now, I want to distinguish, this is not about magnetic field from this material. The material is magnetized, but it's not about the field that it produces. It certainly doesn't produce a 4 Tesla magnetic field. It's about the exchange interaction with this field. Now, you say, exchange interaction, I thought this was an insulator. Indeed it is. It's the exchange interaction just from the scattering of the Cooper pairs off of the surface of the ferromagnetic insulator is enough to kind of rotate them in spin space. The long theory about this, which I won't spend a lot of time talking about. The upshot is that the coupling of a thin superconducting film, and you see that it does need to be thin. This is in inverse nanometers of thickness of the film. So here's 4 nanometers. The scattering of the Cooper pairs off of this ferromagnetic insulator film produces an effective magnetic field, which is dramatically large. These same studies looked at the gap that was induced. And here I want to draw particular attention to the figure caption underneath figure 2, which reads the square of the reduced order parameter. Reduced order parameter just means that they've divided the gap by the zero field gap. It's 1.76 times the transition temperature. Against the square of the reduced field, the field that they've applied in units of the critical magnetic field, so that at 1, the system goes normal. The data points show the different films, and what you're supposed to notice is that for the thicker films, the 14 nanometer and 10 nanometer films, as it reads in the caption, the transition is second order, which is expected from a theoretical calculation. The superconductor normal transition in the Europium sulfide bilayers with a 4 nanometer thick film, aluminum, is first order as indicated by the sharpness of the transition, which means that the gap doesn't really shrink that much as you turn up the external magnetic field, and then it kind of goes bonk. And the data doesn't go exactly bonk, but the first order nature of it is something which matters a fair amount. The first order nature of it is something which has been emphasized in even modern studies. So now moving from here in 1991 up to 2017, and the work from Brambini's working in Francesco Giasotto's group in Pisa, these material collaborators, including Jagdish Mudera, the same guy growing those films, sees this and now a kind of cleaned up version of the data, a couple of important features. This is now the same material, europium sulfide, in a tunneling experiment with thin aluminum, tunneling across an aluminum oxide barrier into a thicker piece of aluminum. And what you can see is that this, again, Tesla scale exchange field, which splits the density of states, can be recognized. And there's two features that I want to point out. One is that the field at which that saturates when you apply a magnetic field is quite small. Here, 30 millitesla of applied magnetic field produces the Tesla scale exchange field inside of this aluminum. And again, I want to just emphasize the same point I already made. The europium sulfide insulator, it's a ferromagnetic insulator, inducing a Tesla scale splitting of the superconducting BCS density of states inside of the thin aluminum in an external field, which is presumably magnetizing and removing the domain structure of the europium sulfide. It's a ferromagnet. In about 30 millitesla, producing this large exchange. That's the one important feature that I want to point out. It only took 30 millitesla to fully magnetize. You know, there was a kind of there was a saturation field of 30 millitesla. Below that, you're only left down here with a remnant field, which is large, but not as large as the saturation field. That's the first important point. And the second important point is it didn't collapse the gap. There's still a good superconducting gap in this density of states measurement. And what this means is that though you've induced a large spin splitting, you haven't collapsed the superconducting gap in a way consistent with this first order like feature where the gap persists until it crashes. So here they haven't crashed the gap, so the gap lives though the splitting is large. Now the theory of this, the order of this transition in which the gap collapses or doesn't collapse depending on the exchange field, and I apologize because every single paper uses different notation for all the quantities, but I'll try to say in words what's going on, is a very old subject here dating back to really, you know, only in the first years after BCS itself, the study of a uniform exchange field on a superconductor was already being studied. And the important point had to do with how the, in this case, how temperature affected this transition. You turn up the exchange field. As the exchange field goes up, the gap doesn't care at all until bonk, you kill superconductivity. As you turn up temperature, again, the gap doesn't collapse that much until bonk, it kills superconductivity. Only when the temperature was sufficiently high, and I'll look at some other criteria for this as well, does it become second order, and you could, in principle, smoothly drive all of the gap all the way continuously down to zero, some crossover point of temperature. But that's not the only crossover point. And here, there's a long, fantastic theoretical history. I'll kind of fast forward to an important review article from last 2019, which considered, and I apologize for going faster than I should. It, of course, is not my work, and I want to get onto the experimental aspects, but it's complicated. How this gap, just as an example, this is what we looked at already. Here was as a function of temperature in units of the transition temperature. So here's zero temperature. And you see that the gap is first order until it goes bonk. That's what I described before. Then you turn up the temperature by moving out this scale. And as you turn up the exchange, now it becomes second order. The red curve is where it hits the axis and superconductivity is destroyed. The gap goes to zero. But out here, it's first order, where the curve would actually be backbent as it was from that Sarma paper that I just showed, and that indicates the first order transition. As you turn up the exchange, that's the graph that I showed before. But you can also do a couple of other things. This is what happens in the presence of spin orbit coupling, and I want to notice that as you move. I'll show you as you move in the in either with spin flip scattering or spin orbit scattering, the opposite things happen. It's probably better illustrated on this graph, where we now look as a function of either spin orbit or spin flip relaxation. You'll notice I'm using the same notation for this tau Sn, where tau Sn is written as the sum of the rates, or inverse of tau Sn is the inverse of the sum of the rates. And beta changes sign depending on whether it's dominated by spin orbit or spin flip scattering. So here, for positive beta, it's spin orbit coupling. For negative beta, it's spin flip scattering. And then you can interpolate in between. But this is the point that I wanted to make. Now, as we turn up the spin flip or spin orbit scattering, here's spin flip relaxation, you can see that the transition in the presence of spin flip scattering can also be driven even at low temperature. Here, the temperature is 1/10 of the transition temperature, much too low to drive the second order. Can also drive the system's second order. And split scattering can also drive the system second order. So this transition about whether or not you have a continuous fall in the gap or whether the gap falls off a cliff when you reach the transition is something which depends on temperature, but it also depends on spin orbit, depends on spin flip. And we're going to need to understand those in order to understand the experiment as it's coming up. I can't exactly do it justice, but just to say that it's a well-studied problem and that the theory is itself well-developed, maybe it's time then to begin to look at data. Should I ask if there are any questions at this point? I see that there are 289 people online, so it's a kind of a risky thing to do, but.
Yeah, there are no raised hands.
Okay.
I do have a quick question though, actually.
Okay.
Before you're referring to a gap, but in the data, there are two peaks.
Yes.
Spin splitting. So is it just the inner gap that's being referred, the inner one that's being referred to here?
Right. In fact, if I can switch out of sequence a little bit, you know, I'm going to just go a tiny bit out of sequence, if I may. This was stuff that I didn't particularly want to show. So, you know, here's this is from a few years later. This is from the 1970s. Here is a zero magnetic field, zero, you know, effectively small spin orbit, small spin flip scattering, and you have a density of states. Now, if you turn on a magnetic field, turning up the magnetic field, you split the density of states. Let's keep spin orbit and spin flip small so that you see this splitting of the density of states. So far, so good. So when they talk about the gap in this case, in that previous study, they were talking about the order parameter magnitude. That is not the same as, let's call it, the gap in the density of states. That's a different quantity, which goes by the letter omega here. And omega in BCS has its peak at 1. Okay, good. So the gap in the density of states is equal to the delta of the order parameter that, you know, that characterizes superconductivity. This peak is at 1. But as you see, that the gap in the density of states in this axis of omega is not 1. One side goes up and one side goes down as you turn on the magnetic field. But it's interesting to look at what happens, at least this is theoretical plots, what happens when you turn on, in this case, spin orbit coupling. Here are the two bands, and you see that their densities of states, they don't go to unity, they change, but they go together now because there's enough spin mixing between the two. And the same thing is true, here's very strong spin orbit coupling, and you see almost nothing happens. I mean, there's almost no two bands. This is now for the case of very strong spin orbit coupling. Similar situation when you turn on spin flip scattering. Here's mild spin flip scattering. This is a non-zero but small number. Obviously, nothing happens at zero magnetic field except a rounding of the density of states. You no longer have the singularity. They split, but they maintain some degree of separation. By the time you turn on strong spin flip scattering, the same thing happens, including the appearance of gapless superconductivity. So now this omega variable, the system still has an order parameter, interestingly. It still has a delta. It's not driven normal, but the omega that describes the gap in the density of states has vanished. So we have to keep all of those different quantities in mind. And I was cheap by referring to just one delta, but that delta that I was referring to earlier on is the delta of the order parameter, not the gap in the density of states. Okay, so good. Let me go back and start talking a little bit about experiment. Before I talk about experiment, I have to talk about the materials that we use. And this was an event that happened. I apologize for forgetting to put the date on this view graph. This is from published, I think 2020. Maybe it was published this year. Maybe it was published 2019 on the archive. But from Peter Krogstrup and his postdoc Yu Liu, and a host of characterization, measurement, material scientists who participated in this. The first study was the epitaxial growth of europium sulfide, this magic ferromagnetic insulator material, directly on indium arsenide. And you can see from the zoom in of this epitaxial interface that the crystals line up perfectly. This was a real breakthrough for the field to grow epitaxial ferromagnetic insulator semiconductor material. It is not exactly what we ended up wanting. We played around with it for a while. Something else catching our interest even more, and that's going to be what we talk about today. And here's a paper which is a kind of a combination between the two. Here you see Yu Liu working closely with Soleil, and also me, Peter, and Cam Moeller working together on a richer combination, a combination which I hope among the 290 now participants in this colloquium, there are enough theoretical physicists to find the, if spin orbit coupling and one dimensionality and superconductivity wasn't enough condensed matter physics for you, add to the ferromagnetic insulator along with superconductivity and strong spin orbit coupling and epitaxial growth. I hope that gives you a headache in a good way. What you see grown here is another transmission micrograph of, this was what we saw before, the europium sulfide directly on the indium arsenide, and now the aluminum grown on top of europium sulfide. The sequence of growth has to be that the aluminum goes on second after the europium sulfide because the aluminum temperature deposition, but nonetheless, so two things to point out. One, whereas the semiconductor ferromagnetic insulator interface is not only planar, but it's in atomic registry, as you can see from this picture. The superconductor ferromagnetic insulator interface is epitaxial, but it is not smooth. There's a roughness to it that kind of bounces along like that. And I think, although it's far from clear, this is now me speculating, that this is going to be relevant for understanding the physics. Is not a perfectly planar ballistic structure. There may be domain structure of the magnetism also associated with this. We don't know. But keep the image in mind. The part of this that Cam Moeller and her lab were involved in had to do with doing a scanning squid measurement. If I go back, I can show you. Oh, I think I chopped it out of this first picture. I'm sorry about that. Cam has a setup that takes a small squid loop and at low temperature moves it around over material. This was on an insulating benign substrate, deposited wires that had the ferromagnetic insulator and the superconductor on the substrate. And Cam can scan the squid with a kind of micron scale resolution. This scale bar is 10 microns long, and see that in fact there is big magnetic fields associated with the ends of the wires. So coming out of the end of the wire are magnetic fields that her team picks up on their squids. And by the time you get up to 20 Kelvin or so, the magnetism is washed out and the thing has disappeared. There's a simulation of what these magnetic fields are, and they're localized to the ends of the wires, this is the right hand axis, which is a logarithmic scale. So for the moment, let's look at the left axis, which is the linear scale, that measuring 1 or 2 or 3 or 4 or 5 nanometers gives these magnetic fields that are rather significant. Tesla's scale magnetic fields, 0.2 up to 0.5 Tesla, depending on where you measure close to the wire, but only at the ends of the wire. So, I mean, this is what you'd expect from a ferromagnet. The north and south poles of the ferromagnet are where the field emerges from a ferromagnet, not anywhere along the middle, as long as it's right. And that was borne out that this is it's not a bunch of domains flipped when this was cooled in an external magnetic field, that it's uniformly magnetized with the magnetic fields only coming out the ends. So that's what's going on with the magnetism inside of these wires. But again, to zoom in, well, that was that again. Let's try to just restart it. I think I'm getting familiar now with it. Shall I press on?
I think so.
Good. Okay, so I want to emphasize there, these are you see a TEM of a few atoms and you start to think everything's perfect. But if you zoom out a little bit and you look at the structure, you see, that's not good, is it? Hey, again, I think we should begin now, since we're pretty far into the talk anyway. We should begin the presentation. So let's take the combination that produced those Majoranas and nanowires and add to it a europium sulfide layer with the idea that we'll be able to produce the kind of ferromagnetic exchange that will act as though we've put the system in an external magnetic field, and ideally create the kind of physics that one could create by putting the thing in an external magnetic field. So here's a cross-sectional picture of the nanowire. It's a hexagonal nanowire, 100 or so nanometers across. Here is a layering of epitaxial europium sulfide grown on the wire, and here is 2 facets of aluminum grown on top of them. The faceting and orientation depends on how you rotate the stage relative to the guns that are putting the stuff on, so you can at will put things on different facets. This happened to be what we put it on for this. And here's what I would like to exhibit first. If you just look at the shell of the device, in other words, let's forget about any kind of tunneling or zero bias peaks or Majoranas or any of that stuff. Let's just look at what's on the outside. What you see is that above a temperature of 800 millikelvin, the material is resistive. The aluminum is resistive. This is just a 4-wire measurement of the full nanowire. Superconductivity in the aluminum is destroyed above 800 millikelvin. Below 800 millikelvin, there's a smooth transition to a superconducting state. In this superconducting state, at the lowest base temperature of the dilution refrigerator, if you try to apply a current, you can find that there's a critical current above which the resistance turns on. Below it, it's zero resistance, and above it, it becomes resistive. Now, the interesting picture to see is how that critical current at which the system becomes normal changes as the external magnetic field is swept. So just, again, nothing about the inside of the nanowire, it's just like a bridge for it at the moment. The critical current of the outside of the system, as the magnetic field is swept to the right, here's the arrow, as the magnetic field is swept from far negative to far positive, it rises, it reaches a peak, and then it quickly and discontinuously falls, and then continues to diminish until the critical current vanishes at about 50 millitesla applied magnetic field. If you sweep the magnetic field the other direction, there's a finite critical current, and just the reverse happens. You go to negative values, the critical current gets very large, and then suddenly it falls continuously to zero. And this has done this in several devices. This is, I should say, this is repeated in many devices, blah, blah, blah. I want to contrast this with the behavior of a system in which the europium sulfide is not in direct contact with the aluminum, where it's grown on different facets And what you see is a couple of things. First of all, the critical temperature is about twice as high. It's a bit steeper, but more importantly, it's about twice as high. And second of all, the critical current, it does have some feature. It does depend a bit on the external magnetic field. And it does have this flip symmetry where it rises and then falls, but it's a very small effect. So if I contrast this with what we saw when the facets overlap, where there's this dramatic feature, with the situation where they don't overlap, where the feature is almost impossible to see, really, and the critical field is higher, one gets the feeling that the overlap between the aluminum and the europium sulfide is where the action happens. Let me do a little bit of modeling to try to understand what this critical current is telling us about what's going on in the aluminum itself. We don't have a tunneling measurement into the density of states of the aluminum. I suppose we could do that, you know, put a tunnel barrier and try to tunnel into it, but we didn't. Instead, what we have is the critical current. But the critical current contains a lot of information. In fact, you can do some theoretical analysis and go from the critical current and how that relates to the critical temperature through this 2/3 power, and infer, wasn't measured, but inferred, a effective critical temperature that, as you see, has these spikes in it, the same spikes that you just get from taking the critical current. The spikes I'm going to associate, if you haven't figured this out already, with the place where the magnetic field passes through its coercive field and has a zero. These are the zeros of the magnetic field where the europium sulfide becomes demagnetized. And during that place where it's demagnetized, as long as any residual ferromagnetic domains are smaller than the coherence length, the superconductor doesn't see all of those disordered domains. It just sees zero magnetization. So it tells us two things. First of all, it tells us that the domain size is small compared to the coherence length, which is correct from what's known about europium sulfide. There was a study by Strambini and co-workers on the europium sulfide grain size that's consistent with this. You can then go from the critical temperature through this Abrikosov-Gorkov mean field theory, which you may or may not like, but this is a good way to go from the critical temperature to what's called the pair breaking parameter, alpha. And alpha has this feature. And if you then say that the alpha, the pair breaking in the superconductor, can be attributed to an effective magnetic field, as if it were a pure Zeeman field, then you can just infer what was the effective magnetic field that was causing this structure in the critical current to begin with. And it doesn't have any parameters, because the alpha that you get is the alpha that tells you what the critical magnetic field is. All you have to use is what is the zero field critical temperature, which we also knew, and that tells you everything that you need to know. So what that tells you is that if this analysis goes through, this mean field analysis and this analysis in terms of associating the pair breaking term with the Zeeman field, that the system feels as if it's in about a 1 Tesla to 2 Tesla magnetic field, except right here, where it crosses through zero when the field flips its direction. So in particular, if you ramp up the magnetic field and ramp back down to zero magnetic field, the system feels like it's in a Tesla. Now, what happens spectroscopically is the interesting part of the story. What happens spectroscopically, we do by doing a different kind of geometry. Instead of putting 4 wires on this, we remove the superconductor at the end. Although we leave the europium sulfide on, we have to remove the superconductor but not etch the europium sulfide, and then put a gate across the end of the device. And when the gate is across the end of the device, we can tunnel into the semiconductor because you can deplete it. There's no aluminum underneath this gate. There's only semiconductor and europium sulfide. And what one sees experimentally is that if you follow, well, you can do a couple of different kinds of curves. Let's change as a function of a back gate, which changes the density inside of the wire, and a cutter gate, C stands for cutter, which changes the depletion of the tunnel barrier, we can follow a kind of an iso contour line called D, or we can follow a cut along C. Let's follow the contour line along D, where you've compensated the change in backgate with a change in cutter so that you follow the same physics along this line. What you see is for an extended range of backgate voltage, a zero bias peak. The experimental signature of a wire on a zero mode occupying this end of the wire, the other being some distance far away. Now, it's not perfect. There are many features in here where it splits and then it rejoins, and it splits and then it rejoins. We learn a lot from this. We learn, for instance, is this an accumulation of many states? Well, no, it's probably a discrete state because an accumulation of many states doesn't have this splitting rejoining feature where it comes back together again. But for much of its journey, it remains a single discrete state between this black band sitting at zero energy in the tunneling density of states into the semiconductor. Let's go on and look at more data. If I sit here at a place where it's kind of about to split and I sweep the external magnetic field, I apply a field, you see that at the coercive field, the place where the field reverses and goes through zero, also the zero bias peak splits. So this is a place where the external magnetic field was just on the edge of being large enough to push this state to zero. And when you go through the zero, the external field, it splits. When you sweep this way at the coercive field, and it splits again when you're going back in the other direction. Then we can play around and do all kinds of studies. We can swing the magnetic field out of the plane. If we go to, again, a place where it's about to split, we see that we apply the magnetic field along the axis. Very quickly, the density of states closes. Interestingly, the density of states of the parent superconductor does not have the same hysteresis as this critical current. Whatever it's inducing in the semiconductor is the same forward and backward. It doesn't have that effect. And we think we understand why, but let me just say phenomenologically, and also that this slope of this line constitutes a rather large G factor. That's probably not what's going on. Probably what's going on is that the europium sulfide is being magnetized fully by the external magnetic field, and that's what's driving the gap of the superconductor to zero. So the gap is already pretty small. The gap is 4 times smaller than the gap of just the aluminum, or the situation where they're on opposite interfaces. Here we can move the magnetic field around. You see that if you go to a place where it's not just about to split, nothing happens. It kind of changes the gap a little bit as the magnetic field goes transverse to the wire. But more or less, if you're along the wire in either two directions and you don't affect the gap, the zero bias peak persists all the way through. And here it is persisting also as a function of gate voltage, although splitting in places and rejoining in other places. There are some interesting effects of when the thing saturates, and that I want to emphasize. You recall that in the Strambini review article, it took about 30 millitesla for the field to saturate. The characteristic of saturating is that when you sweep up and you sweep back, they're on top of each other. Only when you're out of that region and you're in the hysteresis window does forward and backward look different. So here we can subtract forward and backward traces. If we subtract forward and backward traces, we can see at what value of field did the thing saturate and no longer have an open hysteresis window. Well, when the magnetic field is along the wire, then looks like about 50 millitesla in this particular wire, some wires a little more, some wires a little less, was where the hysteresis window closed. And now the two traces were on top of each other. Then you come back, the hysteresis window opens, this one has its coercive field, the other one has its coercive field going up. And over about a 50 millitesla window is this coercive field opened. But now something interesting. If I turn the magnetic field 15 degrees, and then 30 degrees, and then 45 degrees, and then 60 degrees off axis, what you see happening is systematically the coercive field, the field of the size of the window, grows correspondingly. Why? Because the only part of the field that matters is the part of the field that's along the wire. There's an easy axis, and all that's happening is it's getting magnetized along its easy axis, and the out-of-plane component of the field doesn't matter. How do I know? Well, because if I only look at the cosine part of the, if I multiply by the cosine of the angle, that just tells me what's the amount that's projecting down along the wire, it's, except for this point it was a little bit low, it's basically independent of the magnetic field, telling me that wherever I put the magnetic field, this thing has an easy axis, it's magnetized along the axis, the field is coming out the ends, and it doesn't matter which direction I change it. So if you imagine you have these wires now and they're magnetized and they're all over your chip, they're all magnetized along the axis of their wires. They can even be perpendicular to each other, and they'll have effectively Tesla scale magnetic fields perpendicular to each other, because the only field component that matters is the one that magnetizes them along their axis.
Charlie, we have a question from Anton.
Good.
Charlie.
Hi, Anton.
Yeah, hello. So I'm a bit puzzled. I thought that from the previous experiments, we can reasonably conclude that the field misaligned with the wire axis is actually much worse. And even 100 millitesla misaligned of a field that is perpendicular to the wire would basically suppress all of the superconductivity and basically destroy it. Now this seems to be in contradiction.
Well, there are two things to point out. The first is that here, so let's look at two different pieces of data. One piece of data is when you have an external magnetic field. Notice it's only 30 millitesla.
Mm-hmm.
So 30 millitesla swinging around, you know, you'd say that's not really much field to be destroying superconductivity or fooling around with Majoranas or whatever. The Majoranas need a Tesla. So what's happening when you swing the 30 millitesla around is it's kind of helping magnetize or not helping magnetize the wire. Either, in this case, it's magnetizing it the wrong way. Here, it's like 30 millitesla sideways. It doesn't like that. That's against the easy axis of the wire. It kind of, you know, puts domains all over the place and doesn't do very much. But it is important to say that whereas it's just like any other Majorana system, it needs a Tesla of magnetic field to drive with the right G factor the states down from the gap to zero. Now the gap is smaller. The gap is not the full superconducting gap. It's reduced, as you saw from those peaks where it's a reduced gap, probably because of a combination of the Zeeman or this exchange field plus some combination of spin flip and spin orbit scattering that we don't yet know or understand. But it still needs, you know, a Tesla scale field to bring those levels down to zero. In fact, you can see that they're not really adequately being brought down to zero all the time, because sometimes it's not enough to bring them all the way to zero and they seem to split. That's what's going on here. But the field that's swinging around, that's doing this magnetization, is only 30 millitesla. So all it's really doing is dragging the domains around with it.
But I was actually referring to a different effect.
Okay.
So I understand that 30 millitesla is not allowed to create Majoranas.
Right.
But at the same time, in the previous samples, it was well enough to destroy the gap without creating Majoranas, I thought. Or maybe I'm not remembering it correctly, but I thought that the systems that were studied before were quite fragile. You even mentioned it in the beginning of the talk, the alignment of 1 degree with the Tesla field is about 10 millitesla, right? And that seemed to be enough to destroy anything fun. So I understand that the ferromagnet doesn't care and it still provides a strong magnetic field, but for the nanowire, I would imagine this parallel magnetic field is still very much visible and still potentially important. I don't quite understand how to connect.
Yeah, so I guess I'm not sure either, honestly. I'm not sure either. But I think that what I would say would be let's take an example of this system, say not at zero, but like, I don't know, let's move it to over here, say, you know, 45 degrees. What do we think is going on here? I think what's going on here is that there's a Tesla along the axis and 30 millitesla applied at 45 degrees. So there's like, 1.05 Tesla along the axis and 0.05 Tesla transverse to the axis. And you can see it doesn't like it.
Mm-hmm.
It doesn't like it. It doesn't like that 30 millitesla or whatever transverse. And it almost kills it here. It doesn't quite kill it, but it kills it. So I think what you have is, because of this magnetization, the magnetization of the europium sulfide is always along the wire axis, I think. And I think that the 30 millitesla axis just gets swung around. I think that the europium sulfide stays magnetized along the easy axis of its magnetization. And the 30 millitesla does its damage. And I'll tell you, if that was 50 millitesla, it would kill it. If that number right there were 50 millitesla, that thing would go to zero and would totally destroy it. And you're right. This thing hates a transverse field. It's just that 30 millitesla isn't enough. It's enough to do some damage, but I don't think it's enough to totally kill it. If that number was 50, it would be dead at 90 degrees and dead.
But in the next plot, the effects seem to be much less profound. Yeah, here.
Oh, yeah. Well, okay. So this thing is just about the resistance of the wire. This isn't about zero bias physics.
Oh, okay.
This is just about the hysteresis window. This doesn't have anything necessarily to do with myronas. It's just showing when does the magnetization get saturated. And what it's teaching us about is how the europium sulfide likes to get magnetized. It likes to get magnetized only by the field component along it.
Yeah. All right. Thanks.
Yeah. Okay. So to me, that's the end of my presentation. I apologize for all this crashing, etc. And what I'll do is I'll just go back to here and say, this is our first foray into magnetic materials. I'll say that this is the first time, even though I work in the Hans Christian Ørsted laboratory, this is the first time I've ever put H on the horizontal axis of a graph before, distinguishing between H and B. So it's new physics for us. And I think that a lot of condensed matter physicists are a little, if you're like me, you're, a little afraid of ferromagnetism. And, I am for sure. But I think that the important take-home message is, first of all, it's complicated. There's a lot of really interesting physics, but the signatures that we see where there's a really, it's pretty unambiguously clear zero bias peak that persists, occasionally splitting, occasionally doing weird stuff, persists throughout the system, is really very tantalizing and really surprising, and not something that we've ever been able to see with any other kind of configuration of putting things together. This kind of look just doesn't happen by itself. And so there are lots of details that we could talk about, like, for instance, as you open up the quantum point contact, when does a peak become a dip? How does this thing split? And all of these interrogations of what it is that's been formed in this. And it could be a Majorana, it could be a pair of Majoranas, it could be something close to one end. There's certainly disorder in the system. What we can say is that this combination seems to do something pretty magic, and I think is worth our time to consider. And maybe finally, from the point of view of topological quantum information or topological materials, the idea that you can have wires of different orientations, like in these theoretical proposals, each of which carries magnetism along its axis after you magnetize it and then turn the field back to zero, means you really have a new freedom to go fool around and grow things.
Algunas cosas.
So Charlie, we have a couple of questions at this point.
I'm done.
Okay.
I'm ready to take questions.
Thanks, Charlie. Okay, so everyone, I guess we'll do sort of a post-talk question and answer session now. Thanks everyone for attending. Our first question is from Elsa Prada.
Hi, Elsa.
Hello, Charlie. Thank you very much for this beautiful talk. It's been very good. And the subject, I agree with you, is new, and there is this new fascinating possibility to create Majoranas, which is very good. So congratulations.
Thanks.
And I have a question about your, I think it's your slide 25.
Wow. Okay. Let's see. You remembered the slide numbers. Okay. That's my slide 25. Is that the one you mean?
Yes. Yeah. That's
okay. Let me make it full screen again.
Okay.
Okay.
So, well, I think one of the questions that probably many of us have in this field is if what you are seeing here are really Majoranas, meaning these two states at the two sides of the wire, or if this could be quantum dot states at the contact. Okay.
Yeah. So I have a couple of things to say about it. One is that.
Well, let me just.
Go ahead, but maybe you formulate your question.
Yes. So one of the things that I would be expecting if what I see here is a zero bias anomaly that somehow is entering into the topological phase and then going out, because, for example, in your figure D, at the beginning, you have no zero state, then it appears. So I would expect that the whole bands would go to zero, closing the gap, and then reopening, whereas what I see here is what we typically observe when we have these, let's call it quasi-Majoranas or pseudo-Majoranas or non-topological Majoranas, where you have a lone detached state going towards zero. No, this could be something signaling that this might not be Majoranas.
You mean because you don't see gap closures associated with splittings?
Exactly.
Yeah, I think that what's going on, I think that I understand this. I don't think that it's that. I mean, which isn't to say that I know what it is. I think that what's happening is that if I go back to what the structure looks like, I mean, we may want to come back to look at this slide again, but if I go back to, where is it? This picture. The structure is fragile in the sense that the europium sulfide has to induce a nearly killing amount of spin splitting in the aluminum in order to drive those states to zero. So there's almost not enough Zeeman field to bring them to zero. How do I know that? Well, because this thing is not really protected against the Klogston limit. It's not, I mean, if it has some spin orbit from the indium arsenide, maybe, but aluminum doesn't have very much spin orbit coupling. So when the europium sulfide drives this thing close to Zeeman equals gap, it kills the superconductivity in the aluminum. It really will kill it. So there's, I think, not enough magnetic field to keep these states at zero. And that, I mean, maybe this is consistent with what you're saying, is that the system is in a, you know, like it's most of the way toward the field being enough to bring them together. But then when the field is decreased, they separate, but it's not, there's no topological transition at that point. It's in the topological state, but then you just reduce the field. Maybe what needs to happen is a simulation of this where we put in ferromagnetic exchange instead, like Zeeman exchange, and say, would a splitting like you saw in slide 25, how is an event like this one, actually, hold on one second, like this one interpreted? But Ilse, as long as I have you here, there's something that I would like to show you, if I may, and that is, yeah, go ahead, please, go ahead.
Yeah, well,
you keep talking. I'm going to open up something.
Yeah, I was going to mention something else of this slide.
Go ahead.
Which is that, yeah, I was going to ask you, for example, you see that you move VU in device 3, but VL in device 4. I was wondering if you would have such measurements in the same device, because I think the role of VU and VL could be very interesting in the sense that you are pushing the wave function towards the superconductor or not, which I think could give you hints of what's going on there. But apparently,
it's a great question. I don't know off the top of my head. Let me. Actually, I can ask. I don't know whether among the 200 and well, it's 207 now of people on the call, is Soleil on the call?
Soleil, if you're here, can you raise your hand? Via the participants pane on the right. I see him. Okay, Soleil, you're unmuted. You can respond.
Sorry, I didn't catch the question by Elsa.
Yeah.
Hi, Elsa.
Elsa, sorry, Soleil is here. He's the guy who did the experiments. Can you repeat the question?
Yeah, I was wondering if the kind of measurements of your figure, well, I don't see it now. Then
Yeah, sorry, I'll bring it back to the front. That one.
So, for example, E and F, there you are controlling VU and VL, these two side gates. I was wondering if you could have such kind of measurements in the same device, because one is performed for device 3 and the other for device 4.
Right. I think in the supplementary we have example of measurements of VU and VL for device 2, if I'm not mistaken.
That's why I was actually, Soleil, I was just going to get the archive paper and put it on the screen, Elsa, so we can take a look.
Mm-hmm.
Okay, probably you can still see my screen. If I go to the supplementary, Soleil, tell me where to look. Do you remember?
S9 probably. Here we are.
Really, this is really informal.
There are so many.
Yeah, S9. No, S9 something else. Elsa, we'll look it up. We'll look it up offline. Okay. The answer, I think, is maybe.
Yeah. Okay. Okay.
But as long as you're here, Elsa, as long as you're here, I would like to show you something else.
Okay.
Which is.
I just have just one very small thing.
Go ahead.
Slide 25, which is that it looks to me in your slide 25 that you have more other states within the gap. If you zoom it in a lot, I kind of see that there are other states that go down and then up in energy and interact with this zero bias anomaly. And I was wondering if these eye-shaped shapes that you are seeing could be coming from the interaction between this zero energy state and this other higher energy, perhaps quantum dot states at the contact. That's just a comment.
Maybe. You know, we looked around and we wanted to see, does these eyes that you called them correlate with features up here?
Yes.
And then we looked at this one and we said, oh, look, this one's coming down and this one's going up. Look at that. Yes. And then we looked over here and we said, oh, shoot, this one's going up when that one's going up.
Well, well, definitely there are signatures in these zero bias anomalies whenever you have, for example, in D, something going down inside the gap. I cannot point. So in D, for example, you see that these zero bias anomalies have more reddish color precisely when you happen to see something inside the gap, no, approaching.
Maybe.
Well,
yeah, I understand it. And the only other thing that I wanted to show you is this one, which was when we had situations where there was a real end dot state crossing, which looks like a Coulomb state. And we could zoom in on that and see that this particular state, when something like this happens, did not split the zero bias peak in that particular case. When it was not split, I mean, now look, there's plenty of places where it splits, but where it doesn't split, the dot crossing states, which is how I interpret these. This is probably an end dot. And those end dots do that to the state, which is maybe of interest, maybe teaches us something, although I'm not sure what it teaches us actually.
Thank you very much.
Okay, nice to talk to you.
The same.
All right, so we have another question from Beres. Let me unmute. Here we go.
Hello, can you hear me?
Yes.
Yes.
This is more of a comment than a question, so if there's another question, maybe you could take that. But about those splittings, there is one study by I mean, the theoretician was Sergei Provorov, and the experimentalists were Bakers, Plisards, Stanislavskis in 2019, where they did an experiment and the theory on the original Delta experiment. They redid the experiment, but at high magnetic fields, the magnetic fields that your the levels of magnetic fields that your nanowire seems to feel.
Yes.
They see these ubiquitous, going into and out of these things. Those eyes, they see those things ubiquitously. And we also try to do they attribute it to sub-gap states according to their theory. We also try to do something in terms of like a 2D system. And we also see that this going in and out, which the fermion parity crossings, essentially you go into a topological state, non-topological state, etc. That's we saw that in some ideal 2D system with disorder, or a system whose classical dynamics is chaotic. It all depends on the classical dynamics of classical orbits of the system, and you see these things. So I was wondering, I mean, the usual answer is maybe there's sub-gap states, there's semi-wire and etc. But is your system, could your system be considered quasi-1D or almost 2D, depending on the thickness? I just couldn't get the numbers over there. So
yeah, well, it's a complicated system because on one side it's tightly coupled to metal, and so the metal has a very high density, of course, but that metal is superconducting. And then if you ask how many modes are there transverse in the wire, it's a small number. It's probably not one, but it's.
But is it in like tens?
Yeah, I think so. I think it's probably less than tens. I think it's probably.
Oh, okay. So yeah, in those cases, and assuming the system has some either disordered or chaotic stuff, we can say that such a system should show those eyes generically. But well, usually when you do these things, you don't have any disorders.
Will you email me this paper you're talking about?
Sure, I'll email both of those.
Great. The Bakers thing, and then the one of yours.
Yes. Okay.
That would be great. And then we can correspond by email.
All right, I'll do that. Thank you.
Great.
Okay. We also have a question from Tero Hakila. I apologize if I butchered that pronunciation.
Oh, Tero, I've been reading your review articles like like a Bible scholar. So thank you for writing.
Thanks a lot for showing it also, and thanks for the talk. I have actually one comment and one question. So the comment first is about the critical current that you're measuring.
Yeah.
You are associating the critical current with the standard bulk critical current, which you will measure in a bulk superconducting wire, because you are connecting it with the orbital magnetic field. But in small wires, in principle, you could also have another critical current which is related with overheating.
To say it one more time?
With overheating. So that the point would be basically that the current actually generates a non-equilibrium state, and that actually drives the superconducting normal. I was expecting that actually in this wire you would have seen this overheating transition, but maybe this is not the case.
Yeah, I think it's not that, and I think that what I would have looked for in that would have been, if I can go to that slide, I would have looked for a difference between let's call it a retrapping current and a depinning current.
That's true. Yeah.
If I go from and we only have the positive data here, so I can ask Soleil online, but my near certain answer is that if you go from negative through superconductor out to positive, you don't see any hysteretic window.
Okay.
So so that to me is usually where heating shows its
Sure.
phase.
Sure.
So, but let me just, you know, I'm putting myself on the line here. I should ask Sole. Sole, is it the case that when you go from negative to 0 to positive, you don't see a big difference between the depinning and repinning currents?
Sole, you are, I'm trying to unmute. I think you're unmuted now. If you'd like to, oh yeah, here we go.
Okay.
Yeah, there we go.
Yeah, it's as Charlie said. If there is difference, then the difference is, I think, I'm also guessing now, but around 10%. But it was slightly device-to-device dependent, and I think we can attribute it to dissipative lead contacts rather to actual heating effects. But yeah, if there was any difference between retrapping and deepening, then it was very small.
Okay. Actually, the question that I had was that you have, when you showed the structure, you have the Europium sulfide is between aluminum and indium arsenide. But in principle, you could have worked the other way around as well. Does it matter?
What's the other
Probably
way?
matters. That the aluminum is between the Europium sulfide and the indium arsenide.
Oh, you know, there's this stupid thing which drives us crazy, which is that the growers have to put the aluminum on last. So you have this puzzle that you have to play. You can do anything you want, and I'm open for suggestions. You can put it like this, you can put it like that. You can do all kinds of crazy things as long as you follow the rules that the aluminum goes on last. And the reason why, well, maybe there's a super fancy way to do it that doesn't require it, but the reason why is because the aluminum needs to go on at very low temperature, and the europium sulfide has to go on at higher temperature. So if you put the aluminum on first and the europium sulfide on after, it'll desorb all the aluminum and it balls up and falls off. So we weren't able to. Now, you know, there's a lot of clever things that we haven't done yet. For instance, we can have the aluminum on 3 facets. We can have the europium sulfide only under the aluminum. So there's many, many alternatives that we haven't explored yet. We've explored a couple. With the europium sulfide totally under the aluminum, nothing happens. But we could make extremely thin europium sulfide. Remember, it's an insulator, so it's only a monolayer or so that does the scattering. Or we could put more facets or something like that. And if you have some clever idea, the only rule that you have to follow is you have to have the aluminum go on last.
Okay. Okay, thanks.
Yeah, and nice to meet you.
Yeah, likewise.
Question from Marco Valentini, excuse me.
Hello, can you hear me?
Yes, hi.
Hello, so I'm not Marco Valentini, it's not my account, I'm sorry, but I'm very eager to ask a question.
You're going to take off your clothes. It's a Zoom bomb. Okay.
Sorry for that. Oh, yeah, thank you very much for a very nice and interesting talk, but I want to sort of clear one thing. So do I understand it correctly that the field, the effective field that there is inside the indium arsenide is the exchange field produced by the europium sulfide? Is that correct?
I think that that's a short way to say it. If you don't mind, I'll say it a slightly longer way.
Okay.
That the field that's inside the aluminum, the indium arsenide, is the result of a proximity effect from a spin split superconductor. The superconductor has an exchange field in it, and the europiums, I believe that this is true, and it's these data that make me think it, that there's nothing very much going in directly from the europium sulfide. I think what's happening is that the europium sulfide, is that the europium sulfide is going into the aluminum here. It's spin splitting the bands in the aluminum, nearly destroying superconductivity in the aluminum. But what we have is a Tedro-Meserve spin split aluminum here, and that spin split aluminum is then proximatizing the spin orbit nanowire. That's what I think is going on.
So thank you, but do I understand it correctly then? It's sort of aluminum inherits this like spin splitting behavior, and then it proximatizes this delta pairing inside the semiconductor, because this is what matters for my run of physics, right?
Correct.
You should have the Zeeman splitting, but this Zeeman splitting comes from the aluminum. That's what you're telling.
That's my current hypothesis.
Okay.
I mean,
Okay. Cool.
That seems to me to fit the data best right now. But it's not like I got in there and walked around and saw what was going on. All of what I'm inferring is based on the data that I've presented.
Okay. Cool.
Or
Thank you very much.
archive.
Yeah, I think this answers my question.
All right, we have another question from Yoichi Ando.
Hi.
Hey, Ichi, how are you?
Hi, Charlie. Thank you very much for the nice talk.
Boy, this is like going to a party. You walk in, you see your friends. This is great.
Yeah, I have just one question. Yeah, in the introduction, you suggested that the unsmooth nature of the interface between Europium sulfide and aluminum has something to do with the data that you're going to show.
Yes.
But this was actually never presented. So
I didn't really say it. You're right. So let me say what I think was necessary.
Mm-hmm.
I think that there are two features where that roughness plays a role. One is that I think that if the roughness scale is small compared to the coherence length, that it looks like spin flip scattering.
Mm-hmm.
That at zero external field, there's a little bit of domain structure left. I mean, it's mostly magnetized, but we know that it's not fully magnetized. So from the superconductor's point of view, it sees that as a slightly inhomogeneous magnetic field because of the roughness and also because of the domain structure on a scale small compared to the coherence length. If that's true, it acts like, I believe, it acts like spin flip scattering. And the spin flip scattering can reduce the gap and also drive it second order. See, we had a little bit of a problem. We saw a reduced gap. The gap was only a quarter the size of the zero field or zero Europium sulfide gap. But if it was a first order transition, it's very hard to get something that's a quarter the size. Normally it just falls off the cliff.
Mm-hmm.
So the fact that our induced gap was 4 times smaller than the bare gap, I needed to come up with something that allowed it to be a rounded transition so that it could go down that cliff. And I think that the thing that makes it rounded is spin flip scattering. And I think it's from the rough interface. There's also spin orbit. Of course, it wouldn't be a Majorana without spin orbit. And the aluminum does leak into the semiconductor to some extent. But I think that it's the roughness that gives an effective spin flip scattering that reduces the gap and makes it second order.
Uh-huh. Okay, then maybe this enhanced spin flip scattering is the reason why you don't see the splitting coherence peaks.
Correct. I think that that is correct.
Okay, yeah, thank you very much.
Now, wait, let me add, Yoichi, one more thing I want to add, which is that unlike Tedroma survey or unlike the Giazzotto experiments, we're tunneling into the semiconductor, which means that there's also spin orbit coupling that's playing an important role. That can also mix the spin bands. So I think that both the spin orbit of the semiconductor, which is where the tunneling is occurring, and the roughness of the interface that gives an effective spin flip scattering are both at play, and I don't know the ratio between the two.
Okay, alles klar, danke.
There are no more raised hands, but there are 2 more questions. One that was sent to me via chat by Yutaka Shikano, which is the question of whether these devices are stable with respect to thermal cycling to room temperature and back.
Yes.
So, okay, easy answer. And then my question was, also from this era of Tedroma survey, is that these aluminum films, they could help the robustness with respect to field and so forth by adding a little bit of platinum as a spin orbit scatterer in the aluminum. And I'm wondering if y'all have tried playing with something like this to see if that may help you in some fashion.
No, it's a really interesting idea because it's both like poison and medicine at the same time. It raises the critical field, but it induces a kind of spin orbit coupling, which is not always friendly to Majoranas. That is, it's this, it's what they call Elliott-Yaffe spin orbit coupling, where you're scattering off of atoms instead of, twisting like Dressel. So it couldn't be the basis for creating Majoranas, but what it could do is make the critical magnetic field much higher. So the answer to your question is no. You know, it seemed like one thing too many, like europium sulfide and superconductors and a spin orbit atom. It just felt like, you know, someone's head was going to explode. But it would be a way, and I think that there is work going on. Forget about the europium sulfide for a second. But just like if you want to put the thing in a large magnetic field, I think that you can put these platinum atoms on the surface to make the critical magnetic field higher from Elliott-Yoffe spin orbit coupling. But I don't think that it helps you in the Majorana world, except possibly to give you a larger critical field.
Sure.
But as you saw from those gap pictures, it reduces the gap. So it's this funny thing. BC goes up, the critical field goes up.
Yeah.
TC and the gap go down, or TC is almost constant and the gap goes down because of the.
Sure. Okay, I think that concludes our session for today. Thanks again, Charlie. Thanks again to the audience for everyone who's come. For those of you who are still here, I'd just like to put a link in our page on the Long Range Colloquium, and where you can register for next week's colloquium as well, where we'll have video Madhavan of the University of Illinois at Urbana-Champaign. Thanks again, and we'll see you in a couple of weeks.
Thanks, Vala.
Thanks, Charlie.
Yeah, and thanks, Anton. Bye-bye.